Now I'll explain the implementation and live demonstration of our hardware-software co-design system. So this is a Quartus project for the AES 128 hardware accelerator. So the FPGA fabric implements the AES encryption logic while the HPS handles control and software execution. So here I'm opening the platform designer. So also where we load the .qsys file where we configure the HPS FPGA system integration. So this is the QSys file, and since I have already done everything, I'll just explain the steps what all I have covered. So you can see here, this is the component I have created. So just you can see what I have done here. So I have added the AXI wrapper file. This is the top level file, and therefore analyzed and synthesized the file. And this is the slave we are using, Axie4 Lite slave. So yeah, this is the block diagram of it, the wrapper actually. So since we have already added the components and configured the clock and reset signals and all, so we'll just show them here. So we have enabled the HPS system and connected to the FPGA fabric using the lightweight Axie interface. The lightweight Axie interface allows the HPS software to communicate with our AES hardware using memory mapped registers. So we have configured the clock here, reset, and Axie signals required for proper HPS FPGA communication. So after this, we'll just save and click on generate HDL. So yeah, since we have already done it, I'll just explain the further procedures after generating the system. So platform designer creates a .qip file. So which contains the IP integration information. So while pointing to .qip in Quartus, the file is automatically included by Quartus during compilation and connects the HPS system with our custom AES hardware model. So now I'll briefly explain the AES hardware module implemented in Verilog. The AES module receives a 128-bit plaintext, a 128-bit encryption key, and a start control signal from the HPS. The AES core performs AES 128 encryption only as required by the project and returns the ciphertext along with the finished flag. Internally, the design includes key expansion, subbytes, shift rows, mix columns, and so on. And add round key stages. So the encryption runs over multiple clock cycles using an enable signal, so which ensures like proper sequencing of the AES rounds. So next we'll see the AXI interface. So this module accesses the AXI wrapper between the HPS and AES hardware. So here we have memory map registers. So the HPS can write the plaintext, write the key, start the encryption, and read back the ciphertext and status. So this allows clean and structured communication between software and hardware. So now I'll briefly show the main.c file. So it is here. So the software program also generates a random 128-bit AES key at runtime, which satisfies the project requirement. It then reads up to like 16 ASCII characters from the terminal, which form the plain text. So the software performs AES encryption and decryption in C, which acts as the golden reference. So the plain text and key are written to the FPGA using memory map registers, and the ciphertext is read back for validation. So now, since we have like generated the header files and everything already, so this is the header file. Let me show it once. Okay, so you can see the AXI components. The base address is here and the end address is this one. So we just use this to along with the make file, we have compiled it in the terminal, the embedded shell, command shell, and then we have generated the executable file. So I have already connected my board. So I'll just try to now run the PuTTY terminal. PuTTY terminal, I guess. And then so now I'll demonstrate the system execution using PuTTY, and the serial connection is configured with baud rate 115,200, 8 data bits, 1 stop bit, no parity, and no control, no flow control. So I'll just open this now and turn on my FPGA. So I have already inserted the SD card, so the Linux is booting now. So I'll just run few commands and then we'll arrive at the output. So disk L, and now it is I'll just mount this now. And we'll copy the executable file. I have connected the flash drive to the board. So I have to say I have opened PuTTY because I have connected the UART to USB cable from the board to my PC. So yes, we'll just now copy the AES file. I don't know why it's not getting executed. Let's see. Okay, sorry, it's 128. So just a second, and I'm again opening the PuTTY terminal. I had some issue. I think I didn't copy the file correctly. So I'm just running the PuTTY terminal, opening the PuTTY again. Now I have just copied the executable file to my flash drive and I have inserted it again. So let's see, it should work now. So the next command will be okay, so I just mount it. sorry. Oh, what's the command? I think it is media and USB. Yeah, so then we'll just copy. The file name is AS128, yes. And then I think I executed a wrong command maybe earlier, so because of that. So now just change the, see if it's now just so before executing this, I should actually compile this. So I'll just start compiling this. Let it compile, it will take a lot of time. So as you can see, the compilation has been completed successfully. So now we can load the .sof file. Let me, yeah. So first, now the file name, enter, and now we can just open the tools programmer and then close, change file .sof, and just click start. It's done. Now we'll enter this. So I'll just enter my name. So you can see here clearly I just entered a plain text and the software performs encryption as a golden reference. The same plain text and key are sent to the FPGA, which performs hardware encryption. And as we can see, the hardware ciphertext exactly matches the software ciphertext. The software then decrypts the ciphertext and the decrypted output matches the original plain text. So this confirms the hardware software co-design system is working correctly end to end. So this concludes the demonstration of the AES128 hardware software co-design system implemented on an SoC FPGA. Thank you. So I will also just record one more video with one more example. So we'll just run this again. So I love FPGA class. So you can see here clearly the plain text is encrypted in software as well as hardware, and the encryption um, is again sent back to the HPS, and then it's decrypted and it matches the hardware encryption on the software encryption actually matches. So I conclude here that the hardware software co-design project AS 128 works perfectly fine. Thank you.